They don't flap their wings. They don't soar through clouds. And yet, every year, tens of thousands of elite racing pigeons cross borders, oceans, and time zones. Without ever taking flight, they travel in silence, inside engineered crates, tucked in the belly of commercial aircraft or custom freight systems. For the outside world, they're just cargo. But for those who understand what's really at stake, each bird is a neural-guided, precision-calibrated biological instrument, trained for a single, high-stakes mission to return home from anywhere on Earth as fast as instinct allows. Moving a racing pigeon is not like moving a chicken. It's not even like transporting exotic animals or livestock. These birds are biomechanically sensitive. Their internal compass, the avian hippocampus, is deeply dependent on environmental stability. Light fluctuations, engine hums, sudden shifts in temperature or air pressure. Any one of these can suppress the very instinct that defines them, homing. In the competitive world of pigeon racing, that's not just a problem. It's a potential disqualification, a lost investment, a career-ending blow for both breeder and bird. To understand how delicate this process is, think of how gyroscopes are handled in aerospace. Inside rockets or satellites, a single misalignment during transport can throw off an entire mission. The same logic applies here. A top-tier racing pigeon stores its memory of space, not with maps or visuals, but with orientation signals, magnetic fields, olfactory patterns, and barometric pressure traces. Disrupt those signals mid-flight, and the bird may still fly, but it won't know where it's going. That's why pigeon export logistics has evolved into a niche form of transport engineering. Cabin pressure isn't just monitored, it's modulated. Vibration isn't merely absorbed, it's actively dampened through dynamic suspension platforms inside travel crates. Airflow systems are not just ventilated, they're bio-calibrated, based on research drawn from pharmaceutical cold chain logistics, where entire shipments hinge on microclimate precision. In a world where a bird can cost more than a pickup truck, these systems become indispensable. Some of the most surprising innovations come from unexpected places. Mining, specifically from the techniques used to transport explosives in remote regions. In those operations, vibration must stay below 0.5 G to avoid triggering sensitive payloads. That same vibration control technology is now being adapted to pigeon transport, not because the birds are explosive, but because their biological memory, like a gyroscope in transit, must arrive perfectly intact. This isn't a luxury, it's a necessity, because a pigeon that arrives disoriented is not a competitor. It's a feathered passenger with no mission left to complete. That's the invisible pressure behind every shipment. The container must do more than carry. It must protect the bird's neurological integrity, its instinct, its sense of home. And in doing so, it's not just transporting animals, it's transporting potential. The potential of a race, the promise of a return, the story of a flight that hasn't happened yet. It depends entirely on how the journey begins. They arrive on time, they look healthy, they appear calm, but inside, their internal compass is scrambled, and no one notices. Until it's too late. The bird is released at a competition hundreds of kilometers from home. It takes off into the wind, and never comes back. This isn't rare. It's a recurring and costly failure, and the reason often lies in something invisible. Electromagnetic interference during transport. Cargo bays, airport tarmacs, and transitional zones between terminals are environments saturated with signals, some strong enough to distort the avian brain's delicate spatial map. Racing pigeons are not just sensitive to temperature and movement. They are neurologically tuned to the Earth's magnetic field. That's how they find their way across vast distances. But place them in a poorly shielded crate, near wireless routers or radar pulses, and their magnetoreception, the very mechanism that lets them know where home is, can be compromised. This is where innovation has had to meet biology. In recent years, breeders and engineers have developed travel crates equipped with internal Faraday cages, electromagnetic shielding built into the container walls. These structures block external signals, creating a magnetic silence inside the crate, even as the aircraft travels through layered signal zones. But shielding is only half the solution. Inside those crates, temperature must be controlled with surgical precision, not just for comfort, but for orientation stability. The hippocampus, the core of avian spatial memory, is temperature dependent. That's why many top-tier containers include biothermal gel linings. These gels maintain a stable internal temperature, around 20 degrees Celsius, with a margin of plus or minus 1.5 during loading, takeoff, and long-haul flight. That consistency supports mental clarity in the bird. It ensures that when it lands, its internal sense of space and direction hasn't been scrambled by shock, cold, or heat waves. In Belgium, one of the world's most advanced centers of pigeon breeding, a controlled study revealed the difference. Two groups of racing pigeons were shipped under similar conditions, one in standard ventilated crates and one in magnetically shielded, thermally stabilized models. Upon arrival, both groups were released under identical conditions. The results were immediate. The shielded group demonstrated a 27% improvement in homing performance, orientation speed, and return success. It wasn't just comfort. It was readiness, biological readiness, built into the logistics. In 2021, a championship-level pigeon bred in Guangzhou, China, valued at over $90,000, failed to return after a simple regional flight. The investigation traced the problem to a single oversight. During a layover in Dubai, the bird's crate was held on an open tarmac for over an hour, exposed to thermal spikes and rapid humidity change. Inside, the pigeon experienced mild heat stress and signs of overstimulation. Technically, nothing went wrong, but biologically, everything did. The bird lost its orientation, and with it, its future as a competitor. This is the kind of logistics failure that can't be seen with the naked eye, but its consequences are as tangible as any mechanical breakdown, because in this world, transport doesn't end with arrival. It ends with return. And to return, the bird's neurological system must remain intact. If we wouldn't ship a gyroscope loose in a cardboard box, why would we risk a living navigation system, trained for months, sometimes years, in a crate that doesn't respect its design? That question reshapes how we see the pigeon. Not as cargo, but as a system in need of precision, stability, and above all, protection during the most fragile part of its journey. At 10,000 meters above sea level, the air is thin, dry, and cold. For most cargo, this is irrelevant. Insulated crates, sealed packages, temperature buffers. But for a racing pigeon, it's a test of survival not visible from the outside. Even when transported in pressurized aircraft, many shipments neglect a hidden but critical factor: carbon dioxide accumulation. When CO2 isn't properly regulated in live animal compartments, it builds up silently, leading to mild hypoxia, an oxygen deficiency that doesn't kill the bird, but compromises its neurology. The consequence isn't death, it's disorientation, slower reaction time, impaired flight navigation. And for a species whose identity is built on spatial memory, that can mean the end of competitive function. Conventional ventilation systems were never designed for this level of sensitivity. They move air by volume, not by biological demand. That's why the newest generation of racing pigeon crates is borrowing from unexpected sources: neonatal medicine. In modern incubators used for premature infants, airflow is regulated by biofeedback, tiny sensors that respond to the breathing rate of the child. Now, that same principle is being applied to birds. Inside certain premium crates, microfans operate not on timers, but in response to the pigeon's respiration rhythm. The result is a microclimate that doesn't just circulate air, it adapts in real time to the animal's needs. That attention to detail matters because pressure changes during flight aren't always smooth. Slight fluctuations, barely felt by human passengers, can trigger hormonal reactions in the bird's body. A surge of corticosterone, the avian stress hormone, has been observed in pigeons exposed to these conditions. And with that surge comes a measurable drop in navigational performance. In studies conducted by logistics partners in Asia and the Middle East, even minor barometric inconsistencies during ascent were linked to reduced homing accuracy by as much as 19%. One corridor that has become a testing ground for these technologies is the Dubai-Shenzhen route. It's a long-haul journey often used by breeders exporting elite birds to East Asian competitions. On this route, two transport models were compared: traditional ventilated crates versus controlled atmosphere systems. The differences were striking. Pigeons transported with adaptive airflow and thermal regulation arrived calmer, resumed training faster, and reacclimated to local environments up to 3 days earlier than their counterparts. In terms of training response, measured by return speed and altitude confidence, the advanced crate group showed a 40% improvement. This redefines what logistics means in the world of pigeon racing. It's not about getting the animal from point A to point B. It's about what state that animal is in when it arrives. The feathers may be smooth, the eyes alert, but if the internal systems are misaligned, the outcome is already decided. That's why the future of pigeon transport is no longer based on space and time. It's based on biocompatibility. Containers are becoming extensions of the animal's nervous system, environmental shells that preserve its sense of space, rhythm, and direction. Because in this context, transport is not movement, it's preparation. What we see as shipping, the pigeon experiences as memory formation, orientation encoding, and psychological priming. The container is not just a cage, it's a cockpit, and its mission is not just to protect the bird, but to deliver it with its full potential intact. To ensure that when the crate opens, what emerges is not just an animal, but a ready instrument of biological navigation, calibrated for competition. A racing pigeon is not merely an animal in transit, it is a biological instrument, finely tuned to navigate space using internal references most systems can't replicate. Magnetic fields, barometric pressure, olfactory cues, solar orientation, all of these form the basis of its spatial intelligence. When exported across borders, the pigeon carries more than feathers and muscle. It carries a living memory of home. And that memory, fragile and invisible, can be damaged long before the bird is ever released. This is the new frontier of logistics. Crates are no longer just containers. They are controlled environments engineered to preserve cognitive function. Belgian breeders, leaders in pigeon genetics, now design transport protocols that resemble pharmaceutical freight systems. RFID tags track vital signs. CO2 and humidity are regulated by bioadaptive ventilation. Temperature control is kept within a narrow, plus 1.5 degree Sianix margin to protect hippocampal integrity, because any deviation, any spike in stress, pressure, or electromagnetic exposure can fragment the pigeon's neural map and compromise its mission. Between 2020 and 2023, a pioneering corridor between Belgium and Japan tested this approach at scale. Each bird traveled in a crate embedded with telemetry, oxygen flow, vibration intensity, light exposure. The goal wasn't comfort, it was orientation preservation. The result? A 51% reduction in reorientation failure after arrival. Pigeons resumed training faster, with greater homing accuracy and lower attrition. It was proof that logistics could do more than transport. It could sustain identity. The agricultural world knows this logic well. In precision farming, soil sensors are deployed across fields to optimize irrigation and nutrient cycles. But if those sensors are shaken or misaligned during transport, their readings become noise, misleading data that leads to poor decisions. The same applies to racing pigeons. Their orientation data, their ability to read the world, is only valid if the system that supports it remains intact throughout the journey. What emerges is a shift in perception. These birds are no longer passive cargo. They are autonomous navigators. Each one functions as a biological sensor crossing international skies. They measure, interpret, and respond to environmental signals in real time. And like any high-sensitivity instrument, their integrity depends on how they are handled before activation. This transforms the role of freight from a support function to an active part of competition. Because the pigeon's outcome isn't only determined at the starting line, it begins inside the crate, inside the hold, hours before flight. Every vibration absorbed, every magnetic fluctuation blocked, every breath supported by smart airflow. These are not luxuries. They are performance factors. To see pigeons as birds is to reduce their value. To see them as precision devices, as mobile, memory-driven organisms, is to understand the level of engineering required to preserve their function. In this perspective, the cargo hold becomes more than a transport zone. It becomes an extension of the bird's brain, tasked with maintaining its sense of space until the moment of release. And that's where agro-logistics becomes something more profound. Not just movement, but continuity. Not just delivery, but calibration. Because what takes flight at the end of the journey isn't just a pigeon. It's a system, biological, cognitive, and engineered, that has remained intact across borders, time zones, and machines. A flight that begins long before takeoff and only succeeds when everything else has done its part.